Hi, for our senior design project this time, our team creates an automatic shut-off valve. I'm Dhanushika Velagadhar and we have another two members in our team, Jason Dickinson and Austin Sir. I will move on to the first slide of our presentation, the introduction, and I'll talk about it. Uh, the purpose of our design project is to create an automatic shut-off valve for Chart Incorporated in New Prague, Minnesota. If you talk about Chart a little, Chart manufactures and design cryogenic equipment and they supply liquid gas. So our task was to create an automatic shut-off valve for their bulk tanks. So this is how the current system works. While in the filling process, when the tank is full, there's a tricoque valve at the bottom of the tank. So when the tank is full, it spews out the liquid, letting the driver know that the tank is full. So when he sees liquid coming out of the bulk tank, the tricoque valve, then he goes and shut off the supply manually. So when the valve we created is installed, I'll just run through it quickly. My colleagues will explain it in detail in the next slides. So when the valve we created is installed, when the tricoque valves spews out the gas, we keep an cryogenic temperature near the tricoque valve. When it detects the desired temperature, then when we know the tank is full, it sends a signal to an Arduino controller, activating a stepper motor and shutting off the valve. And if you move to the next slide, the objectives. First, Chart wanted it to be 100% mechanical, but we saw the filling process being done, and in winters it cannot be like 100% mechanical, so we had to use little electrical system for the valve we are creating. And the other thing is because we are dealing with really negative temperatures and high pressures, the safety is an important fact. So we made sure our materials that we use are up to the standard and that can withstand the pressure and the temperatures. So after we get our valve to be installed in the bulk tanks, it will make the driver's job much easier because the manual work the driver needs to put in is reduced. And similarly, there will be no excess gas leaking out of the spitter valve.
I'm Jason Dickinson. I'm going to expand upon a few points that Danushka had brought up earlier. First off, the specifications. When Chart initially brought this project to us, they told us that they wanted a fully mechanical system, and we were given a budget of $1,500 to work with. In order to keep our costs down, we decided that everything was going to be manufactured in-house. We ran with this particular mechanical design from September of 2019 until January of 2020, when we saw an actual bulk tank getting filled. This led us to our current electromechanical design, which is shown here. This system will incorporate a removable power source, a battery pack, that will power our microcontroller. Austin will expand upon this in the later part of the presentation. Next, we got our constraints. As you can see here, safety was our number one constraint. This product had to make the filling process safer for the truck driver, or it was not worth even looking into. Secondly, this had to work in cryogenic temperatures, specifically around negative 320 degrees Fahrenheit, which is for liquid nitrogen. Thirdly, this product had to be externally mounted since it would be going on bulk tanks that are currently in the field, and Chart wanted to use this as an aftermarket accessory. Fourthly, somewhat tying back into our first constraint, we could not increase the pressure on the tank. If we were to increase the pressure on the tank too much, we could cause an explosion. Lastly, this could not add too much extra work for the truck driver. If we added too much work, the truck driver would not want it, and the company might not purchase this product.
For our engineering process, we started by defining the problem, which was creating an automatic shutoff valve that was all mechanical. We then went into looking into prior solutions for problems that were similar to ours. After looking into prior solutions, we went into designing our own solution that was all mechanical. Once we believed that our all mechanical design was foolproof, we went into calculations and actually seeing the filling process for our problem. Once seeing the process, we noticed that there would be environmental factors that we did not account for in snow and freezing rain that could cause too many issues with an all mechanical system. We in turn had to go back to the drawing board and redesign our solution to be an electrical mechanical system. Then we went into testing our subsystems and would have followed this by testing our whole system with all subsystems put together, and went into refabricating it to make it more factory ready and testing our final prototype. For our subsystems, we had a spring return handle, a Arduino, a RTD, a servo, and a trigger. Now only 4 of the 5 were able to be tested due to us getting our trigger the week after spring break and nobody was able to go and pick it up. So our 4 subsystems that were able to be tested have all passed and will all work great. So it is also assumed that when putting all of the subsystems together now, that our whole system will work. For our impact, how will this help truck drivers? Well, it will increase the safety as they will not have to be near the tricock valve to close it as liquid is coming out of it at very cold temperatures. We also had a budget of about $1,500. Our final cost of our system was $916, saving around $584. This will also help company sales per part on part for tanks. It was $916 for our part to be made. Previously, Chart had talked about selling this product for $2,000 to $3,000, bringing in a profit of roughly $1,000 to $2,000 with our product. Thank you.